Thank you. I will begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I thank you, Lord, again for these students. I pray that you be with us today, Lord, to help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. All right, so today I will tell you some very interesting things from Chapter 8 of Gamelin. Hopefully today we will end with a proof of the fundamental theorem of algebra, which does not involve a contradiction. It's actually a constructive proof. It's pretty cool. So section 8.1 is on the argument principle. The argument principle. This is not some sort of relationship advice. It's math. Let's see here.
Oh, good. I was confused. I thought it was like 150.
Oh yeah, it's like 150. When I'm interviewing like potential new students here, I apologize profusely for the existence of that course on the DCP. I'm so sorry. I tried to remove it, but we don't have such power. One day, with the right provost or the right dean, maybe we'll strike it from the list. It's really helped you. It's really helped you in Landon. Ooh, I like it. Now you're playing along. You realize that doesn't make me stop. Yeah. Suppose F is analytic on D, and for a curve gamma such that f of z is non-trivial on gamma, we say 1 over 2 pi I, the integral over gamma of f prime of z dz over f of z is equal to 1 over 2 pi I, the integral over gamma of d log f of z. This is the so-called logarithmic integral of f of z along gamma. Okay, so for example, consider f of z equals to z minus z naught to the n power. All right, for some integer n. And I want to consider a curve. And we haven't, today is we could have been, there's something we haven't talked about much, maybe not at all in this course. And this is something we could have been talking about for a while now, and that's the concept of winding number. So here, the curve we're going to consider, gamma, is parametrized as follows. Gamma of t is equal to, z naught plus r e to the it for 0 less than or equal to t less than or equal to 2 pi k. For some k in the integers. Now, I don't really think 0 is very interesting. I suppose you could consider k equal to 0, but that would be kind of stupid. So, what is the meaning of k? I mean, this is a circle, right? It's centered at z naught. Excuse me. And you're out here. You start at this point, z naught plus r, right? And then you go round. That's k equals 1. Then here's k equals 2. K equals 1 to 2, right? And then here would be k equals 2 to 3, right? And so forth, and so forth. And so if I have k equals to 10, that means you're covering the circle 10 times, right? You go from 0 to 20 pi. If k is equal to minus 3, then you cover the circle 3 times, but in the clockwise sense. right? So k positive counterclockwise, k negative clockwise. But, you know, so the k is what's called the winding number for the circle. It's the winding number of gamma. Okay, so let's calculate the logarithmic integral for this function around the circle. What do we get? So we got 1 over 2 pi I, the integral along gamma of, let's see, what's f prime of z? It's n times z minus z naught to the n minus 1 divided by f of z, which was z minus z naught to the n, dz. What's that work out to? 1 over 2 pi I integral what do we got? We got n dz over z minus z naught. Am I right? Hey, what is that? You're like, well, that's a Laurent series, right? Centered at z naught. Right. So, of course, we can apply Cauchy's residue theorem, you know. But the thing is, when you do that, Cauchy's residue theorem we did for a simple closed curve, right? So you actually have to apply Cauchy's residue theorem, you know, on each circle. Cover, you know, like each positive k gives you one residue, right? I mean, each counterclockwise covering of the circle gives you a positive residue. Each counterclockwise gives you a positive residue. Each counterclockwise. We stated Cauchy's residue theorem for counterclockwise curves that were going once around, right? If you go back to Cauchy's residue theorem and you prove it again for a curve which is closed but has some non-trivial winding number other than 1, you just take the residue and multiply by k in this case. So this is, I mean, or you could just calculate this directly. It's up to you. 1 over 2 pi I, there's an n, and then I got 2 pi I k. If you don't believe me, just plug in the parametrization. You can work it out in like 3 seconds, right? Fine. You guys, your silence is weighing heavily on me. All right, so z minus z naught is what? We've got n r e to the I theta d theta, dt rather, e to the I t dt, and this is integrating from 0 to 2 pi k, and downstairs we have r e to the I t, the e to the I t's cancel, the r's cancel, we're left with n over, and there's an I upstairs, I've forgotten the dz, the i's cancel, we got n over 2 pi, and then this all breaks down to t, evaluated from 0 to 2 pi k. And so there you have it, nk. Which, of course, is what this simplifies to as well. Okay? What's the significance of nk to this function f of z? So if I look at z naught, right? Here's my curve gamma, right? However many times, I don't know, I'm assuming k is greater than 0, okay? What are the, if you look at f of z is equal to z minus z naught to the n, how many zeros of f of z are within this curve gamma? I mean, this, you know, f of z has z equals to z naught as 0 of order n, right? So if we set k equals to 1, then this integral, the logarithmic integral, just gives us the number of zeros for this function within the curve. Okay, we'll move on here. In fact, that's a theorem, which we'll prove. Theorem. This is the argument principle 1. And it states the following: let D be a bounded domain with piecewise smooth boundary partial D. Boundary partial D, and excuse me, let f of z be meromorphic on D and its boundary. D is a domain, right? So it's open, so it doesn't have its boundary in it. What does it mean for it to be meromorphic? What does it mean for the function to be meromorphic on the boundary and D as well?
It's analytic except at singularities where they're either removable or full.
Right, it's analytic everywhere except for where it has singularities, and those singularities are isolated in their poles. Right. Okay, so we also assume that the value of the function on the boundary is non-zero. Okay. Then this example generalizes essentially. 1 over 2 pi I integral over the boundary of D of f prime of z over f of z dz is just equal to the number of zeros minus the number of poles, counting multiplicities. So in other words, counting multiplicity means that if I have a 0 of order 5, then n sub naught is 5. If I have a pole of order 20, that makes n infinity 20, right? So double poles count more than simple poles, et cetera, et cetera. Here's proof. Now, nothing about winding number here. Of course, you could state this. All these theorems we're doing today, you could put a wrinkle in. You could state them for a curve with non-trivial winding number. We're not going to do that, just like we haven't up to this point. I should mention, you can give generalized versions of most of the theorems we said in here by adding a winding number. Okay. Anyway, so let's suppose z naught is 0 of order n. Then what? That means we can write f of z as z minus z naught to the nth power, right, times some h of z with h of z naught not equal to 0, right? So what does f prime of z look like in this context? It's n times z minus z naught to the n minus 1 power times h of z, right? Plus what? Plus z minus z naught to the n power times h prime of z by the product rule. Then we calculate the quotient. So f prime of z over f of z is equal to what? I should have written the derivative first. Oh well. So you got to divide this by that, right? So the first term gives me a n over z minus z naught. Do you see that? It's almost the same calculation we did in our example. But then there's another piece, right? Plus what? H prime of z divided by h of z. Do you see that? See, because when we divide this summand in f prime of z by z minus z naught to the n, the z minus z naught to the n cancels, and then you're just left with a quotient of the derivative of h by h. Now, what did we assume? We assumed that f was not equal to 0 on the boundary. That makes this quotient reasonable to look at, right? All right, so then what? Where is z naught, by the way? Z naught is the 0 of order n, right? And we're also assuming that z naught is an order of n inside the boundary of D. I mean, that's the idea here. So if I can picture D, z naught's in here somewhere, you know. I guess D doesn't have to be a simply connected domain. It could have a hole or something, you know. I guess that's possible, but all right. Then what? What happens if we do look at then 1 over 2 pi I, the integral of f prime of z over f of z dz? What do we get over the boundary of D? We can calculate this by Cauchy's residue theorem, right? And what is the residue? 1 over 2 pi I, right, times 2 pi I, n. So it's equal to n. What's the other thing we should consider?
Pole of order n.
Right. Suppose z naught is a pole of order n. Then f of z looks like what? F of z looks like, let's say, g of z divided by z minus z naught to the n power, right? With g of z naught not equal to 0, and g of z is analytic at z naught, right? Now then what? F prime of z looks like what now? You got yourself, I'll write it as, I'll use the product rule again, g prime of z over z minus z naught to the nth power, right? And then minus n g of z over z minus z naught to the what? To the n plus 1 power, right? So we can calculate the quotient again, f prime of z over f of z, and we get, looks like g prime of z over g of z, right? And this time, minus n over z minus z naught. So, I mean, the critical observation here is just that the residue of f prime of z over f of z at z naught is equal to plus or minus n, with the plus for the last case, right? And the minus for the current, for a pole, right? So if I go through, if I do the integral again, I get minus n here for the pole. You guys with me? So now we just do the general thing. So put together these two cases we've looked at. If you think about D having, you know, Z1, Z2, ZK, it has these singularities or zeros. then if we look at 1 over 2 pi I, f prime of z over f of z dz, what do we got? Well, by Cauchy's residue theorem, we've got 1 over 2 pi I times 2 pi I, the sum, I equals 1 to k, let's say j equals 1 to k, of the residue of, f prime of z over f of z at zj. What is it? Oh. So, I mean, what is this? Well, it picks up n, right, for each pole of order n, and it picks up minus n for each, it picks up n for each 0 of order n, it picks up minus n for each pole of order n, and it just adds them together. The 2 pi i's cancel, and you're left with what we claimed, which is n0 minus n infinity, where n0 is the total number of zeros up to counting multiplicity, and infinity is the total number of poles counting multiplicity. Okay, so there's a way to understand this. So if we let's try to understand this a little bit more intuitively. Intuition for the argument principle. So what is what's the log, what's log of f of z? It's the natural log of the modulus of f of z, right? Plus I times the argument of f of z. Now here, of course, I mean this to locally indicate the selection of a branch, right? I mean, I don't want to commit to a principal branch or any particular. I want to talk about all of the branches of the logarithm at once. Just we can do that. To understand this locally has to break down to one of those choices. Okay, so what happens then if you think about the differential then of the log of f of z, right? It's the differential of the natural log of the modulus of f of z plus I times the differential of the argument of f of z. And just think about it. If f of z is, were you thinking about your future life? I mean, I saw Sharon. She looked very happy. She looked at peace. Oh, you were stretching your neck. Oh, okay. Well, that's less interesting. Anyway, so f of z not equal to 0 tells me that this piece is exact. I mean, if f of z is not equal to 0, then that's the differential of a function, which is defined over the whole curve, right? If the boundary. So by the fundamental theorem of calculus, that piece will integrate to 0 as we go around gamma. Think of gamma being a simple closed curve, right? And so that piece goes away. And what is the logarithmic integral really calculating? It's just calculating this piece, really, right? This is the piece which is giving a non-trivial contribution. And so I can rewrite this. Oh, sorry, making a mess of things. I can rewrite that as simply what? The i's cancel, right? I think I'm left with a at the moment I think I'm left with a 2 pi. This is equal to 1 over 2 pi integral over gamma of the differential of the argument of f of z. Or you could write it this way. It's the net change in the argument of f of z divided by 2 pi. Or we could take this and rewrite argument principle number 1 as argument principle number 2, which states the following: the integral over gamma of the differential of the argument of z, argument of f of z. In other words, this is the net change in the argument of f of z, okay? It's equal to 2 pi times the number of zeros minus the number of poles counting multiplicity. So the net change in argument of f of z as we trace out gamma. And there you go, that's the argument principle number 2, which is actually computationally the way to go. You guys with me? No? Yes? Yes, no, maybe so. So, for example, let's try this out. Here, I'll try to do something not in my notes. Well, maybe I shouldn't. I've got a picture in the notes for what. I'll get out the notes here in a second. Let's look at a different example. What if we looked at, say, f of z equals to z to the z to the 4th plus 1, right? And we study gamma, which is parametrized as follows: gamma t is equal to, let's say, 2 e to the it, 0 less than or equal to t less than or equal to 2 pi. You guys with me? So let's try to use the argument principle number 2 to count the number of zeros that this function has within the circle of radius 2. Right, so this is circle radius 2, centered at 0, right? Now, I already know the answer for this example. I already know the example. The answer should have 4 zeros, right? Because the answer is that we should get, I mean, I even know what the zeros are here. Z to the 4th equals to minus 1, so therefore z is an element of the 4th roots of minus 1, right? Those are all on the unit circle, so they're inside this. We should find 4. How does that flesh out? Well, what you have to do is you have to look at the function, right? Evaluated, look at f. We have to look at f of gamma of t and study its argument, right? So what is f of gamma of t here? It's 16 e to the, sorry, I'll write a step here, 2 e to the it, I raise that to the 4th power, I add 1, which is what? That is 2 e to the 4 it, right? Oh, I'm sorry, 16 e to the 4 it plus 1. I think this is going to be a good place to use Euler's formula. So this is what? This is really 16 cosine 4t plus 1 plus I times the 16i times the sine of 4t. What's the argument of this? I mean, this is actually kind of difficult. What I actually have to do is to imagine plotting this curve as t ranges from what? From 0 to 2 pi. I don't think I want to try to do that without technology, honestly. So let me write that over here. I have x is equal to 16 cosine of 4t I have y is equal to, oh, plus 1, right? Y is equal to 16 sine of 4t. Can you guys see geometrically what that is? I mean, I don't know what that is right off the top of my head. Let me seek professional help. Oh man, why didn't I write it over here? Idiot. Oh, by the way, the Bernoulli numbers, like the Bernoulli number problem in your last homework, I was working it out this morning. Golly, his definition of Bernoulli numbers is non-standard. I don't know if you guys noticed that or not, but I was really confused with it. Like, what? What is? Oh, he's defined b sub 1 to be b sub 2. B sub 2 is actually b sub 4. B sub 3 is actually b sub, I don't know, it's complicated. It's silly. Okay, I was doing something, wasn't I? Okay, so come on. Can you get the lights for me? So we had what? X equals to didn't like me to do. How do you do that? No, that's not what I want.
I think you just need it in a different line.
I do? Okay. See, because I want,
Oh, unless that gives you a different curve.
that's what I'm afeared.
Can you do like x comma y is equal to, can you do it vector equation?
No. No. I'm trying to. Come on, stop that. Curses. Sorry, I'm trying to. How do I? Oh. How do I change the upper? There we go. I want 0 to 1. And all right, well, it's kind of silly the way I'm doing it, but you get to see there's nothing else going on, right? It's just tracing out. Looks like one time around, huh? Wait a minute, but hmm. It's all fun and games until I actually try to do an example. I tell you. So I said man, what did I have? I was looking at z to the 4th plus 1. And what did I say it should work out to? I've covered it up now, but oops. The net change in the argument was supposed to be equal to 2 pi. So it looked to me like
Oh, you know what I bet it was doing?
what?
How about it was retracing the curve 4 times, but you can't see it?
I think I'm hoping that's what was happening, but oh, right!
Yeah.
Okay, so, man.
You did like a little dot.
I know. My point is, to actually study the progression of the argument, you have to be more clever than I am today. Okay, that's obvious. All right, so if I had done that, we should have seen that the argument was progressing through, see here, 8 pi. If we did it carefully, we should find 8 pi in the example I've covered up now. And then divided by 2 pi would give us 4. Sorry, I seem to have failed at illustrating that for you. This one, z cubed plus 1. Again, I look at f of gamma of t, I get e to the 3it plus 1. If you look at a circle of radius 1, a circle centered at 1 with radius 8, then if you follow the argument, you should get. Why would you get 6 pi?
Well, this example, it's 3.
Yeah.
Can't you just evaluate it at t equals 2 pi and 0 compare the angle?
Well, but that doesn't.
Because I know directly it's not holomorphic, right?
Right. Well, here's
So
another.
that's equal to f prime of z over f of z, which is holomorphic, right?
You really have to follow the argument and see what it does. I mean, because you can't follow. I mean, you can't just look at endpoints because you can go from branch to branch. That's the problem. I can't just look at endpoints, unfortunately. This one, I have. Excuse me. So here I have. I'm looking at the circle of radius 1 centered at -1. And but that's not what this picture is, right? I'm saying that's the curve. If you look at f of the image of the curve under f, you get this funky thing, which looks like this. And if you study the evolution of this curve, it goes like like that. And so, in fact, it increases a little bit, maybe up into like 45 degrees before it swings back into the negative, right? And then it goes all the way around and comes back to here again. So if I was just to look at the endpoints, I would get 0. But the net change here is actually 2 pi for this one. So just 1, 0 falls within that. With just 1, 0 doesn't fall within this, just 1, 0 falls within this curve, which is what makes sense because we're looking at the function z cubed plus 1, which has, it has zeros at -1 and the other, the zeros are here, here, and here, right? I'm looking at the circle of radius 1. So we're looking at this circle. It only has 1 0 in it. And that's why when you carefully study the argument, as I have not been able to do for my example I covered up here, you'll get 2 pi for this one. Okay. I'm just saying, if you're like me, you got to be careful to not confuse there's two curves going on here. The one is that you're trying to analyze the number of zeros and poles inside, right? You don't actually graph that. That's the weird thing. You graph, what you want to do is you want to graph the image of that curve under the function. And then that you just need to study the argument of, to figure out the net change in the argument as it traces out. The winding number issue is unavoidable here too. That brings us to Rouché's theorem, which fortunately I have just enough time to tell you about. Rouché's theorem states the following. Let D be a domain, a bounded domain, and with smooth, piecewise smooth boundary. We look at two functions, f and h. They're analytic on D and its boundary. We insist that the modulus of h of z be less than the modulus of f of z. I think of h of z as like a small function I'm adding. Well, anyway, I think of h of z as being small relative to f. And the theorem is this, then f of z and f of z plus h of z have the same number of zeros in D. In other words, you can take the function f and you can perturb it by adding this other smaller function h, and it doesn't change the number of zeros for f of z inside D. The proof is pretty simple. If you read through it, basically what we do is we just take f of z plus h of z and factor out f of z by writing h of z over f of z. Now, f of z is assumed to be non-zero on the boundary, and this term cannot be, in terms of its real part, could not be larger than 1, which means that the total real part of this has to be positive. That places the term in square brackets on the right half plane, which means that if you study the argument of this piece, it is governed just by inverse tangent, the standard branch of the inverse tangent. So around any simple closed curve, the argument increases by 0 on this piece, this whole piece. On the other hand, if you look at the argument of f of z plus h of z, it gives you back the argument of f of z, because the argument, again, of this 1 plus h quotient piece, it always goes back where it started on any closed loop in the half plane. So then we apply the theorem we've been talking about today to see that the number of zeros matches. Because there's no poles here, we assume that f and h were analytic. Well, in order to, it's a propositional thing, right? So we're assuming. Oh. Here's a picture of what's going on. You could think of, like some people think about the h, the perturbation function, as sort of like the leash, and you could think of f as kind of being like you're walking along the image. I don't know how to say it. Kind of like a dog on a leash or something, but who cares? That's you can read this and come to your own conclusions. The theorem is what it is. Let's use it. So here's the great application of it. You have this 11th order polynomial, all right? Z to the 11th plus 12z to the 7th minus 3z squared plus z plus 2, all right? I want to analyze the number of zeros within the unit circle for this thing. So basically what you do is you take a look at it and go, aha, hey, that 12 is super awesome because that 12 is way bigger than anything else in there. And you can see if you define the f of z to be 12z to the 7th, well, that's easy. I know how many zeros does 12z to the 7th have within the unit circle? What are the zeros of 12z to the 7th on the complex plane? Can you analyze this? Z equals 0 is the only zero, and what's its order? 7. Okay, yeah, this is not a trick question. That's easy. That's the point. Pick on that. What's left over is h of z is z to the 11th minus everything else, right? Minus 3z squared plus z plus 2. But if you look at the modulus of h of z on the unit circle, it's at most 1 plus 3 plus 1 plus 2. What's that? 3, 6, 7. It could be at most 7. It's probably not even that, right? So clearly the modulus of h of z is less than the modulus of f of z. There's a modulus sign missing here, right? Sorry about that. And therefore, by Rouché's theorem, this polynomial has 7 zeros in the unit circle. You see how this makes nice test questions? Yeah. Right? Because if you tried to solve this problem without Rouché's theorem, it's pretty easy for me to test whether or not you know Rouché's theorem, right? Because to solve this problem without Rouché's theorem means that you'd have to factor that 11th order polynomial. That seems unpleasant. This required relatively little mental energy on our part, right? I think the argument counting is much more complicated than this. You can also use it for things other than polynomials, though. Here's a standard example. Prove that the equation z plus 3 plus 2e to the z equal to 0 has just one solution in the left half plane. What is that one solution? I guess we don't even need to know it. The idea here is to look at z plus, well, e to the 2e to the z is what? It's e to the x times e to the iy, right? E to the iy is unimodular, modulus 1. E to the x, that's harmless in the left half plane. That's at most 1, and it goes to 0 as x goes to minus infinity. So this e to the z term is small in the left half plane. This is the perturbation. Now what's the order of z equals, z plus 3 has a 0 of order 1 at minus 3. So all you got to do is find a curve, and basically so we just look at this half circle, make sure the radius is big enough to apply Rouché's theorem. It turns out as you study it, you need to have r greater than 5. If you have r greater than 5, you then have that the modulus of z plus 3 is, and it's pretty easy to see that from the outset, right? The modulus of z plus 3 is greater than the modulus of 2e to the z, provided that, z is at least 5 from the origin. That gives you 2 plus 3 is 5, which is clearly bigger than this other thing. So you need z is 5. So you need r is equal to 5. And then you can apply Rouché's theorem to see that there is, in fact, just 1 0 in this half circle for the perturbed function z plus 3 plus 2e to the z. And then you let r go to infinity, and that gives it to you. Which is, here's the rest of the argument. Sorry, I wasted so much class time on the silly example. And finally, as I advertised at the start, here is a proof of the fundamental theorem of algebra, which is both constructive and simple. Consider the polynomial p of z is equal to a to the n, the usual, just an arbitrary nth order polynomial, where a sub n is not equal to 0. The idea here is to study Rouché's theorem for this polynomial on a circle of radius r. And we want r to be big enough that we can think of the leading term, this a sub n z to n, as the sort of the dominant function, and the rest of it as a perturbation. Now, how do I know that the modulus of a to the n, z to the n, it dwarfs the modulus of the rest of it added together? Well, if you just think about that, the modulus of the first piece depends on the nth order of r. The modulus of this is something like the modulus of, something like r to the n minus 1. And then you've got some other constants coming into play, right? But those constants are insignificant as you let r go to infinity. Eventually, you got to get to the point where this is like, if r is like 1,000, this is roughly speaking like, 1,000 to the n minus 1, whereas this is 1,000 to the n. Well, 1,000 to the n is way, way bigger. Anyway, so it stands to reason by some simple inequalities that the modulus of h of z is this, is less than a to the a sub n times r to the n, if r is sufficiently large. So then you can apply Rouché's theorem to say that the number of zeros for this polynomial is the same as the number of zeros for this polynomial, but the number of zeros for a to the n times z to the n is manifestly n. There you have it. There are n zeros for a complex polynomial in the complex plane. I like this argument a lot because it's constructive. It doesn't rely on some contradiction like the rest of the arguments we've had for the fundamental theorem so far. Anyway, thanks guys. I'll see you Friday.